Welcome to the June bonus episode. We are going to make these cone-shaped pieces. This one is sort of the right size for the center of a daffodil, but you can do all kinds of interesting things if you have some bigger ones. And if you go back and think about the December or January bonus episode, I can't remember which, where we talked about curvature, you'll notice that this cone, and strictly speaking, this is a cone with the piece cut off of it, and so it's called a frustum. Just a cone with a horizontal slice out of it. Has remember, two curvatures, right? One is just the circular radius around, but the other one is completely flat. The other direction is completely flat. So that's a zero curvature direction. If you recall, the Gaussian curvature is the product of the two curvatures. And if you have a zero curvature surface, you can cut it out of a piece of paper. Now, strictly speaking, there's a little complication. They talk about how locally you can cut it out of a piece of paper, which means that your actual shape, if it's complicated enough, you might need several pieces of paper that you glue together. And if you want to see what shape makes that cone, I'm going to give it a white background, right? It is this sector of a circle. So there's a common radius, there's concentric circles, and two radii that you've cut out. And so let's make one, and then I'll show you some of the math to help you generate exactly the type of cone that you want. So I've got this piece of it's Bristol paper, a little bit thicker than cardboard. So I've got a center for my compass marked out. I'm going to draw a circle, and then with the same center, I'm going to draw a bigger circle. Whoop. Okay, I went crazy there. Okay, so I won't use that piece. Right, and then I'm going to put my ruler starting from the same center point. I'm going to draw a radius. Okay, and I can't use that spot where it kind of went funny, so I'll draw this radius. So there you go, I got a sector of these concentric circles. I'm going to cut that out. I'll cut out the inner circle, and I'll cut out the outer circle. And then I can fold it around and attach it with a piece of tape. Okay, squish it around a little bit so that it takes the shape. And there you go, a nice little cone. Now, where the math comes in, which I'll do in my sort of classroom technical style, where the math comes in is, you can just play around, trial and error, draw some circles until you get the shape that you want. And if you really like it, you're going to use it more than once. Make a template and then copy it out onto the pieces of paper you'll actually use. But wouldn't it be nice to just describe exactly what you wanted the cone to be? And I would say it would be the inner radius, the outer radius, and the height. you'd want to specify those things and then draw the arcs that you need to make that happen. And I'll show you how to do that. It's a two-step process. There's a way to specify or to work out what the radii and the height will be. And then there's something called an inverse problem, where then you work out the radiuses that you draw on the piece of paper and the angle that you cut out to get the shape that you want. Okay, details coming up. Okay, before we get to the math, I wanted to show you something fun. I got this giant compass on Amazon. It makes me very happy. And with it, and some big pieces of paper, I made the templates for a vase. There's a base, and then the vase part. This is just the template. Of course, I made it out of cardboard, and then covered it with paper mache. If you are willing to get a big compass, you can play around and make up all kinds of different shapes, and then do some paper mache on top of them. Okay, now on to the math. Okay, I'm set to do some math for you. Before we start the main computation, I have something I'm going to show you about a way to measure angles in radians. So you know that if you've got something like this with the right angle, there's an angle here that's 90 degrees. And you can take your protractor, that's that thing that has the angle measurements from your high school geometry set. You can measure out other angles in degrees. And so that's ultimately what you want, is to find some angles in degrees for our cone project. But there's another way to measure angles, which is you take a sector of a circle that has the angle that you want, and I'm going to call that angle theta. This is a typical thing you call angles once you get to high school. And we're going to measure this angle in radians. And that would give you theta is this distance, I guess I'll call it capital A, divided by this radius. And so you can see, right, that if you want to convert, you can have a big angle, right, which is 180 degrees. And then this length, if this length is 1, so it's a circle of radius 1, this will be pi. And so the conversion is pi radians are 180 degrees. So if you want your angle in degrees, you'll take your angle in radians and multiply by 180 degrees and divide by 2 pi. And for our computation, I'm sorry, factors of 2, okay, divide by pi. Let's get that right. Okay, there we go. And for the purposes of our computation, using this is a symbol that you can use to represent an approximation. you can just use 3.14, and that'll be accurate for what you do. Although many calculators have the pi button, and you can get the result of pi to many digits. So we're going to work out an angle in our cone problem in radians, and then to convert it to degrees so that you can use your protractor. This is what you do. Okay, so let's make a start. There's two parts to this process. First of all, I'm going to go with one of these things that we did. We've got a radius, another radius, and an angle. And again, I'm going to use theta for this angle. And I'm going to say, well, here is one radius, and here is another radius. These are things that we did with our compass and our protractor. And I'm going to go one way, right? Which is to say, well, if you did this is the trial and error part, right? If you did this and then you wanted to know what kind of cone comes out, right, then this cone has a radius on the bottom and radius on the top, and height h. I'm using little letters for these targets. Okay, and so now we want to work out what R1, R2, and little h are in terms of the theta, the R1, and the R2 that we can actually implement on the paper. And one of the things you can do right away is to see there is a distance here, which is 2 pi r1, right? That's the circumference of a circle with radius r1, and that's got to be the same as this length. So that's going to be theta r1, right? And that gives us r1 is theta r1, capital R1 over 2 pi. Okay, so now you know that if you cut out that shape, you would know what the bottom radius was, and it's exactly the same computation to get the upper radius is that. Okay, and now I'm going to do a blow up of this picture. Okay, and I'm going to make it just on this drawing, this thing here, except I'm going to do it this drawing. Sorry, this drawing is the one I'm going to do. Okay, so let me draw that a little bit better. Right. The triangle on that side is right. It's got this height h that I want. I know that this length, let me get another color. This length has got to be this length, right? And so this has got to be R2 minus R1, that big length, right? And then this one, it's going to be this thing here, right? I got R1, R2 up there. This one is going to be a little R2 minus little R1. Okay, and then from this, I can do Pythagoras. So I tried to do this, and this would tell me that R2 minus R1 squared is the same thing as h squared plus R2 minus R1 squared. Okay, and that would tell me, well, what do I want to work out? I want to work out what h is. So h squared is going to be R2 minus R1 squared plus minus R2 minus R1 squared. Okay, and that's not quite what we want, right? Because, of course, we could work out R1 and R2 up here and then put them in here. But we want to have formulas for all the stuff that, how the cone turns out in terms of all of the measurements that we made making up the template. And so I want to write that this is the same thing as theta R2 over 2 pi. And this is the same thing as theta R1 over 2 pi. Okay, and then interestingly, this is just a multiple of R2 minus R1, the same as this one. And with a little bit of algebra that I can do in my head, this is going to be 1 minus theta over 2 pi squared times R2 minus R1 squared. Okay, and so with my R1 is theta R capital R1 over 2 pi, and my R2 is theta R2 over 2 pi. I can now work out, after I take a square root here, right? I can work out from what I cut out over here, I can work out what shape that I get out. And so I'm going to call this the forward problem. This is the problem where you've drawn something, an R1 and an R2 and an angle, and I am telling you what a shape of cone comes out of that. Okay, but this is not the problem we actually want to solve. This is the trial and error problem. We want the inverse problem. That is, you want to tell me what the cone is going to look like. So it's lower and upper radius and its height. And then you want the algebra to tell you how you should make the template to get that shape. Okay, and this gets almost, I mean, we're doing some high school geometry and algebra, but this gets, you know, at least some distance along the way of some of the things I do for my research work, for my day job. And that is, I look at some forward problems that are much more complicated than this, where you can't find a solution, you know, with algebra. You have to do some computational approximations. These are problems that come from physics and chemistry. And the computational methods get a little bit tricky. You know, work out how to get a good approximation to your problem. And then, of course, it's even trickier when you want to do some inverse problem, where you want to figure out you know, from seismic measurements, what kind of structure there is under the earth, and whether it might have, you know, oil or uranium or whatever in it. But here we can make progress with algebra. We can get exact solution. Okay, and where I'm going to start is, so here is my forward problem. I'm going to start with a little bit of a variant on this equation for h. Remember, in the problem we're going to solve now, h, little r1, and little r2 are going to be given. So, of course, these are pretty simple relationships, right? If you knew theta and someone told you little r1, then it's easy to work out capital R1, the thing that you actually implement. So theta is really the thing we've got to work out. And what I'm going to do, right, is to do the algebra I did for this one, right? And instead of doing this replacement, I'm going to do the opposite. I'm going to say that this is a little r2. Oh, I've got some notes. This is little 2 times 2 pi divided by theta. And the same for that one. And so now my h squared, it's basically the same kind of algebra I did before, is going to be 2 pi divided by theta squared minus 1 times little r2 minus r1 squared. Okay, and now you can see things that we're given are the little variables, right? The little h, the little r2, the little r1. These are the way we want it to look. And so now I just have to do some algebra to look at what theta is. Okay, I'm actually quite good at algebra. So I'm going to go, my first step is going to say I'm going to have 2 pi over theta squared. I'm going to do a couple of steps at once. So I'm going to have an h squared divided by r2 minus r1 squared. And then I've got to add 1, right? And just to, I don't know, I can bring this to a common denominator, right? Okay, and now I'm going to invert this and take the square root. Again, I can do 2 steps at once. I'm going to have theta is 2 pi. Then I'm going to take the square root of the inverse of that thing. Oh, and there's a square, so I'm going to get r2 minus r1 divided by the square root of h squared plus r2 minus r1 squared. Okay, and then this is almost all of the way to our inverse problem. You are telling me the shape that you want, so you're telling the little r values, h value, and then I can do this work to work out what the angle is. And then, of course, once I get the angle, I can work out what those 2 radiuses that I draw with the compass in terms of this angle that I worked out and the radii of the top and bottom part of this frustum that I work out this piece of a cone. Now the good news is this is in fact all implemented on a nice website where you can type in R1, R2, these little values and theta. No, sorry. Yeah, you can type in the little r1, little r2, and h values that you want, right? And it actually prints out the template for you, which you could just cut out. Now, of course, that means that you may want to make a cone bigger than what will fit on a piece of paper that you can print out. But you can always go to the print store and say, I want my regular piece of paper, blown up by a factor of 2. Make sure that they don't distort it in any way, so uniform increase. Or like me, you can go on and buy a big compass. I'll put a link up to that website. That's not my site, but it's very fun. It's got these cones that we're doing. There's also a bunch of other curvature 0 shape templates that they have there. You can explore and have some fun. And maybe next month we'll use those to make a vase for the flowers that we did this month. Okay. Enjoy July. I will be back. I'm going on vacation. So I'll be back at the middle of the month, and I'll pick up a project on the bonus for July.